I'll be watching you very carefully during the course of this lecture to make sure no one dozes off.
There's a fire alarm there, I could just.
Okay. Yes, yes.
Yeah,
Yes.
be triggered.
It's going to be triggered at any moment for anything. All right, so I thought what I would do in the second lecture is really concentrate mostly on laboratory rotational spectroscopy, and specifically give you a little bit of background about various techniques that people use to detect molecules in the laboratory. It doesn't necessarily have to be focused on astrochemistry per se, but obviously that's what the focus of this workshop is about, and the example I will show you is very much aligned with that. Just generally how we can make molecules, some of the strategies and the techniques that we use to detect molecules, and then really spend most of the time talking about a specific example, which I think is certainly very relevant to astrochemistry, in which we can ultimately detect a molecule in the laboratory, we can do all the spectroscopy, and then we can find it in space. And the key point is here is we're not stamp collecting. We want this discovery to have actual impact. On the basis of this discovery, we can learn something about an astrochemical or astrophysical source that we didn't know about the processes that occur there. So that's the basic outline. So again, I'll just quickly talk about rotational spectroscopy. The key here is how we can discover something entirely new and be very confident that we've detected the rotational spectrum of something. All right? And that's really fundamentally driven by the fact that it's a structure-based tool. Basic principles, production methods, the role of ab initio theory. So this will expand a little bit on what we talked about the other day, strategies, and then mostly time on this case study, which is disilicate carbon. So it's a triatomic molecule, right? It's a pretty simple molecule, but it's somewhat deceptively difficult in terms of its how it was came about to be detected in the laboratory. All right, so this is a view graph which, you know, it's when people talk about their work, they always put themselves in the center, right? Because everything else has to float. No. But the point here is, you can see it better on the projectors, but what, again, astrochemistry or astronomy in general is driven by remote sensing, and so we, in order to understand the phenomena that we see in terms of light, emitted or absorbed, we need to understand the molecules, their excitation and their properties, so that we can infer all sorts of different phenomena in space, right? We can understand kinematic motion if we understand rest frequencies, we can look at high-Z observations. The point is star formation, looking at molecules maybe moving inward, so their relative velocities and forward. And there are many other things that we can do, provided that we understand the spectrum of these molecules. And arguably, there are three basic points that we have to address if we're going to detect types of molecules that we see in space in the laboratory. The first is we have to have a means by which we make them. All right. Now, many of them are stable, or at least some of them are stable, so we can synthesize them. But most of them are not. They're reactive, they're ions, they're radicals, they're things that we can't easily synthesize. So we have a variety of production methods that we need to use, but we have to make them in enough quantity whereby we can detect them. If we produce them, we have to have sensitive enough instrumentation to actually detect their lines, right? And so we'll talk a little bit about that. You always, when you do a microwave experiment, a rotational experiment, you get lines, right? And you have to have some strategy for actually figuring out amongst potentially a forest of lines which ones are due to the molecule that, or due to which molecule, and specifically the molecule that you're seeking to characterize. And so that's, each one of these is, I'll talk a little bit about how this is done. And there's no really rigid formula for how this is done in many respects. All right, so it's important to emphasize that, in fact, there are many, many examples where laboratory astrophysics actually came after the radio astronomy. The classic example is HCO+, right? Bill Klumper proposed, in fact, this was the carrier, and it wasn't until some years, 5 years, 6 years later, that its laboratory spectrum was measured. And there are many other examples, radicals and other things. We often have found them in space. We've been reasonably confident as to their identity, but the laboratory spectroscopy has lagged behind. And that's because most of them, especially the larger ones, are exotic in nature, right? You can't synthesize them. They're generally either unknown or unfamiliar to laboratory chemists or physicists, react very quickly at the launch on rate in many cases. And so this has been a challenging point in terms of production and ultimately the instrumentation used. The key point here is they don't come with labels, right? We see lines, even though rotational spectroscopy is highly redundant, and among these force lines, we have to have a way of connecting different lines that are due to the same molecule. The lines in space may be faint or they may be highly uncertain, based solely, for example, on an ab initio calculation. So that would require, if we didn't have laboratory spectroscopy, either deep integrations or very wide spectral surveys. This is increasingly an issue because telescope time is competitively given out. And so if you go and you write a proposal and you want to use a GPT and you want to look for some new molecule in space, and you say, well, I have an ab initio calculation, and that ab initio calculation is good to 1%, you're not going to get much traction because there are many, many lines that will fall within that 1%. Right? So if you have an accurate rest frequency, you then can know exactly where to look, and there's no ambiguity in terms of the assignment. All right. Some of the advantages. Now, again, if you wanted to take new molecule in the laboratory, you could argue that you really shouldn't use microwave spectroscopy at all. You should actually use optical spectroscopy because, again, the Einstein A coefficient is much, much greater. The U-cube factor is much more favorable. But, of course, in space, typically molecular clouds are very cold. And so it's the rotational levels that are going to be populated, not the vibrational or even electronic degrees of freedom. So in some sense, we're stuck doing rotational spectroscopy. But it turns out there are a lot of advantages of rotational spectroscopy, even compared to optical detection. One is it's a, as I think most of you know, it's a highly resonant technique at low temperature and pressure. So in space and in the laboratory, we can achieve very low temperatures and very low pressures. So we can do very complicated chemical analysis if we have the tools to actually assign things. So this is a somewhat conservative estimate. I estimate that in a very low temperature, a few Kelvin, at very low pressure, using rotational spectroscopy, it may be possible to take a mixture that has as many as 10,000 compounds simultaneously and analyze them using this technique. By comparison, gas phase, GC, mass spec, which are the two most widely used techniques today, can differentiate about 100 compounds. 100. And a lot of effort has gone into making them more, trying to make them adaptable to more complex mixtures. So rotational spectroscopy potentially has 1 to 2 orders of magnitude greater discovery space than do optical, these other techniques. It has many advantages in the sense that it's highly robust. Unlike optical and infrared, there are many effects like predissociation, internal conversion, and there are all sorts of things that can happen when you excite a molecule electronically that are bad in terms of detecting it, right? So you can't, if you use remedy spectroscopy, I don't know if many of you know what that is, but you do 2-photon excitation, produce ultimately a positive charge. You can detect single charges. You can have highly sensitive optical methods that are available that are much more sensitive than we can do with rotational panels. But there are problems with that because many molecules may not be amenable to that type of spectroscopy. The other issue is that unlike rotational spectroscopy, which is related to structure, if you take an ab initio calculation, or you can even take Pauline's book, and you can normally estimate the rotational constant of rotational spectrum to a few percent solely based on standard bonds and angles. And certainly with the calculation, you can do better than that, right? If I asked you, well, what's the correlation of the optical transition of a molecule and its structure? There isn't any, right? I mean, a molecule could be large molecules and small molecules can have transitions in the visible spectrum, right? So there's no correlation. Your ability to predict theoretically the optical spectroscopy of the molecule is actually fairly poor, regardless of its size. Unlike the radio spectrum, which is much more precisely. And ultimately, that's because, again, it relates to moments of inertia, it relates to the number of atoms and the location relative to the center of mass. And we can, in fact, take the intensities and we can readily convert them to abundance because it depends upon the vacuum moment and the partition function. So two things that we can know very accurately from the rotational temperature and at least theoretically from the vacuum moment. So during the past decade or so, I should really say probably now 2 decades, but it's really been an incredibly, rotational spectroscopy has really been emerged as a very, very successful technique to detect all sorts of these unusual exotic molecules. And in our laboratory, we've lost count, it's probably at least 300 have found in the laboratory. Maybe 10% of those have now been found in space. All right, so I won't belabor this point, but again, the point here is that the frequency of the transitions are highly diagnostic. Yes?
Yeah, the slide on advantages and perhaps some of the disadvantages.
The disadvantages, the disadvantages were listed but not highlighted. So there are two main disadvantages. You have to have a dipole model, right? So you cannot detect a molecule that's not whole. Having said that, there are lots of ways around it, right? There are isomers. Benzene, for example, has many isomers, full beam, which you could use, if you will, as an indication of the existence of benzene, perhaps. You can tag things, right? You can create a dipole moment that. But nevertheless, for purely non-polar species, you can't detect it by this method. The other issue, again, is the issue of sensitivity. It has high sensitivity, but it doesn't compare at all to the most sensitive optical techniques.
But what about the confusion? Rotational spectrum?
Well, the confusion limit where? In space or in the laboratory?
No, in rotation.
Well, I don't know. In the laboratory, I don't think we've reached the confusion limit.
No, but
but potentially, I mean, that is an issue. But that's, I mean,
the higher the resolution.
Well, the high resolution, like I said, in the laboratory at low temperature, low pressure, it's incredibly complex mixture analysis can happen. And optically, it's not at all true that would be possible, that level of sophistication. But nevertheless, at high pressure and higher temperature, rotational partition function becomes a big. So that's why, again, because of the redundancy, it's highly desirable to have low temperature and low pressure. All right, so just going back here, right? So again, ultimately, the transitions, if we look at a simple rigid rotor, depend upon well-defined changes in the quantum number and quantity, which is related to the moments of inertia. So by isotopic spectroscopy or what have you, you will fundamentally change the rotational constant and the transition frequencies, and we have very high resolution, so we can easily distinguish between carbon-12 of a species and carbon-13, for example. All right. So what are the key deliverables that we have by rotational spectroscopy? Ultimately, we can unambiguously establish the existence of a molecule, its identity, and potentially its structure if we have enough information, right? That may be otherwise difficult or impossible to establish in theory or models. It's not really the point of this presentation, but by deriving these quantities, we can improve actually theoretical models by calibrating them. And this is important, again, for large chemical models and other combustion models, for example, where we want to predict outcomes in final products. The key here is that we are using this data ultimately to look for molecules in space. Right? So you want highly accurate rest frequencies. And we ultimately can use this information, or it can be used, if we produce a molecule, we know we can derive its abundance, we know the conditions under which it's made, and that is a firm foundation for other people, potentially, to undertake investigations in other wavelengths to characterize the species. All right, so there are two basic measurement techniques that are widely used in the field. This is one that you should all be familiar with, taken in chemistry, right? This is Beer's law. We basically have a light source, we have an absorbing medium, we have a path length, and we have a concentration. And this is widely used. Absorption spectroscopy. It's a non-resonant technique, so we change the wavelength of radiation, and we simply look at the amount of intensity and what is absorbed. Generally speaking, this is not done at very low temperature. It's typically, the coolest ones are rotationally cold about nitrogen, so you might cool the cells on the wall. The wall cells down to liquid nitrogen again to help the partition function, right? So the signal is proportional to the square of the dipole moment in this measurement, and that is also true in space, right? We're looking at the emission as opposed to dipole moment squared, and there are frequency modulation, as mentioned, I think by Daniel, was used, or maybe it was Susanna, to get away from the 1 ref So we modulate, and we might increase the path. For example, we could put a mirror here and reflect the light back, or we could use multi-pass cell because the signal is proportional to the path. All right. The other technique is very simplified show here, and that's called Fourier transform, which is a very, very widely used technique today to look at the rotational spectrum of molecules. The idea is you simply have a short pulse of radiation. So the classic analogy is that you hire some very good Italian tenor or something like that. You have a series of glasses which have different amounts of water, and they simply start doing this ascending chirp. When you get resonance, they'll crack your glasses, they're good, right? And that's exactly what we're doing here. What we're simply doing is we have a short pulse of radiation, and we are trying to coherently excite these molecules with their characteristic rotational frequency. All right? If we do that, that's a short pulse, and in the measurement, it will sing, so to speak, for a much longer period of time. So we can distinguish this coherent macroscopic polarization from the initial pulse because it has a much longer time scale. All right? We take the numerical Fourier transform of that, and we get the power spectrum. There are two variants of this, which are called, I think, well, I guess I'm not going to show that just yet. But there are, I'll talk a little bit more about those in a minute, but there are various ways to produce molecules. The easiest way, well, the hardest way, depends on how you do it, is if you can actually synthesize a molecule, right? That's not, again, it's not realistic to think for many of these molecules, that's practical, right? But in the early days, you could in fact make molecules, stable molecules, and then measure their rotational spectrum. So that requires that you actually be a good chemist. The joke is there's two types of chemists. The good ones are bartenders, and the bad ones are bouncers. I don't know if that's actually true or not. The other joke is, a lot of the chemistry is this highly saturated carbon chain chemistry that we see in space. The joke is half of the German chemists who were really big into acetylene chemistry either had one hand or one eye because it's highly explosive, right? So you have to be very careful. Nevertheless, you can, if you have a certain level of acuity, you can do this. The advantage is it's high yield, but only a small number of species really can be done this way. The other approach, which is widely used, and Susanna's group and Lucy's, among others, use various, if I call it, resistant synthesis. Basically, you have two reactants, and in one case, you're going to make something that's chemically reactive, so that the reaction will be driven forward. So Susanna's group is doing this in the insertion reactions, which you mentioned yesterday, these Boyden ovens that you resistively heat the metal, which otherwise doesn't have a vapor pressure and a temperature. You heat it up, and then it reacts with some other simple precursor, all in this one product. All right. Here's an example, actually, of the direct synthesis. Again, this was done by Harry Proto before he went to Rice and discovered C60. He actually synthesized these long-chain polyions, HC3N, HC5N, and ultimately HC7N. And this is the spectrum that he measured here. He notes in the paper the decomposition rate of the cell was rather fast. Okay, these observations indicate that the laboratory spectrum of HC9N would be very difficult. Literally, he synthesized this, and as he was measuring its spectrum, it was reacting away, right? So that's a pretty, I'm not aware of anyone in recent times that actually has attempted to resynthesize this because it's highly unstable. But it's just at the edge of what you can do. But again, you could, yes?
What does it react with? Itself? Or?
Yeah, I mean, it's just, again, it's a highly unsaturated system, and it will react away. Just like acetylene or diacetylene at high concentrations, yes?
But is it possible to isolate this stuff in traps and keep them isolated from other molecules in order not to be so reactive?
Under the right conditions, yes. You potentially could do that now. Exactly. Yes. I mean, in trap, you have to think about how to do that. But there are a number of ways that people use traps now that were not in existence, obviously, in this time. So another technique that's used is microwave discharges, whereby, again, it's kind of an assisted method, so to speak. You take some small molecule, you run it through a discharge, disassociate this precursor. In this case, you form fluorine atoms, which then can be react with some other precursor, and you can abstract hydrogen atoms, as an example. Right? So Free fluorine is a little tricky to work with, right? Fluorine in general is work with, but it's a very good abstraction agent for organic precursors. And again, this is kind of the assisted method where in 1 or 2 steps you can hopefully synthesize the molecule you're seeking. The disadvantage of it are side reactions, and often fluorine will not only abstract, it will add. And again, now you have a molecule that can be a byproduct which is quite polar. Right? So this is an example where we have a cell, and we're doing a symmetric kind of arrangement here, and we have a dihedral mirror, so the radiation is coming in here, bouncing, rotating upon reflection, and then over here we get it. Okay. So this was used by us many years ago. It's been used by many other people as well. So you take a very simple reaction in which fluorine atoms will react with methyl cyanide, and you will produce 2 radicals, H2CCN and HCCN, and this is a spectrum of HCCN. It's a very clean way to make HCCN radical, which has a triplet sigma ground state. And we did a spectroscopy way back when, trying to understand the fact that it's actually a quasi-linear molecule. It's not, this hydrogen is not, has a very shallow bending potential. Okay. Another widely used technique is laser photolysis. Again, so you have to produce something in the gas phase, but the idea is you, with a, usually an excimer or a YAG laser, at a fixed frequency, you choose a precursor, typically with a fairly weak chemical bond, like a bromine or iodine atom or fluorine, and you pass the laser light, in this case, through this cell, as shown here by Auger, and it disassociates your precursor. That can then subsequently react and ultimately yield the product that you're seeking. That can be tricky as well because, again, it's hard to control. Once you start this process, all of the possible side reactions, but it can be a very clean way to make some species. A more common technique now is laser ablation. Lucy mentioned this yesterday. This is a widely used technique for essentially any, in the chemist sense, metal, right? Things that don't have any vapor pressure and room temperature, right? So you can take a wide range of metals. You take a rod, which is shown here. You bring in, again, a buffer gas and perhaps some precursor. You have typically a YAG laser, could be an excimer laser, and you synchronize the opening of the gas pulse with the laser itself. It will then ablate this material, and it's entrained in the gas. Reactions occur in the thorium expansion and produce, in this case, metal-bearing molecules. It's been widely used by, again, many groups to detect these refractory species. Examples include magnesiums, calcium, and titanium, among others. The tricky part of this is that, first of all, rarely is the ablated material atomic. It may come off as an atom, it may come off as globular clusters, what have you. The other issue is that the YAG laser has typically these have 10, 20 nanosecond pulses. The beauty of rotational spectroscopy is that, again, you're running at fairly low wavelengths, so you have a very large active volume compared to what you do at optical wavelengths. So you typically have, like in a cavity experiment, the active volume is about the size of a grapefruit. It's quite big, so you can produce a lot of molecules in this, if you can fill it. Right? The problem with a 10 nanosecond laser is that you're only producing molecules, relatively speaking, for a short period of time. So if you want to fill the cavity, you'd ideally like not 10 nanosecond laser, you'd like a 1 millisecond laser, right? But in fact, when the chemistry happens, this gets broadened out. It's not 10 nanoseconds anymore. It's significantly longer. But there's a filling factor issue that can be a problem in these laser experiments, where you need to actually produce the molecules for a longer period of time. Okay. But nevertheless, it's been used by good success. This is an example from our group where we did TiO2, which was ultimately found in space, where we measured a variety of transitions. We could make it either by ablating titanium and then passing oxygen across it, or we could take titanium dioxide, which is interstellar sunscreen, so to speak, right? and ablate it, and you can produce all these different isomers. Of course, the beauty of these heavier elements is they have multiple isotopic species that have significant abundances. And so these are just some of the spectra that we measured, and again, the transitions that are shown here. I think the most widely used method today in the field is electrical discharges. Many people use this. These have been very extensively studied, not because of potential spectroscopy, but because of the lighting industry. There are several modes of operation. There's the so-called positive column. This has been reported with very good success for many species, radicals, carbene ions. It's non-specific. You can produce many different things. It's not really understood exactly the series of reactions that necessarily yields various species. And it has all these different characteristics here, but most of the molecules are thought to be, at least the neutral molecules in this positive column. And again, these have been very extensively studied from the light industry as to how the electric field gradient changes from the anode to the cathode and the potential.
Mike,
Yes.
could you go to the previous, the
Yes.
titanium oxide? So how do you distinguish the different isotopes?
They have characteristically different rotational spectra.
Can you see it? I mean, in this,
Oh,
you can measure the isotope shift.
absolutely, yes. Yes, it's many, you know,
Is that-
examples.
is-
These are this, I think the same line, these are exactly the same line. So this is 73% isotopic.
No, percentage
Yeah.
or concentration?
No, that's a concentration. What I'm saying is, but my point is it's the same transition. And you can see this one is at 8,000.
I see, okay, I see.
This one is, so again,
Okay.
the feature width here is maybe 100 kilohertz, or 100 kilohertz. And these lines are separated by tens of megahertz. So again, it's just a delta function here, 10, 20 megahertz down, it's another
Yeah.
delta function. Frank DeLucia actually, many years ago, showed that you could alter the characteristics of this discharge. And by doing so, you could actually enhance the production of positive ions. And so the idea here is he applied a magnetic field over a significant fraction of the discharge between the anode and the cathode, and thereby extending altering the IV characteristics. The idea being that, go back here, that many of the positive ions are produced right here in the negative glow region. By applying a magnetic field, you can ultimately shift so that the negative glow extends significantly longer than the positive column now is shown. And what he showed in this series of measurements is that, I think it was, I can't remember the molecule, I think it was M2H plus or something. But you can see here as he applies a greater magnetic field, the signal intensity of the line goes up by between 1 and 2 orders of magnitude. Right, so that's another method, depending on the species that you're seeking, that you could adopt. All right, so we did that. We had done coordinated SO2 at low frequency, and then we ultimately measured its millicurie lines again, so that we can confidently look for this in space. And this is just an example. We did not see 2 orders of magnitude, but we did see a significant difference in applying this magnetic field and altering the IV characteristics. So most of the rest of the talk is going to focus on these 4 transform methods in combining with the supersonic molecular beam. So this has turned out again to be an incredibly powerful way to characterize molecules rotationally. This was a technique developed by Bill Flegier in Illinois in the mid-1980s. So the idea is you have a high Q cavity. Typically, again, we're in the radio band, so we're not talking about small mirrors. We're talking about mirrors that could be a foot or 2 feet in diameter or more. And you can, by setting up this cavity, you ultimately, fairly good surface accuracy, you can achieve very high Qs, a few tens of thousands. What that means is that the bandwidth, the instantaneous bandwidth of this device is actually very narrow. It's about no more than a megahertz, typically a fraction of a megahertz. So we only get a tiny amount of data at each setting of this device. But we can, computer control, we can sweep, synchronously tune the mirrors and change the applied frequency, and we can stitch together little pieces of spectrum to make a wider spectrum. The key point here is, again, this is operating at a few, let's say 10 gigahertz or so. So we need to couple to a source where the rotational lines are very strong at that frequency. So you can produce now supersonic molecular beam, or you can buy commercially these supersonic molecular beam sources. General Valve in particular is widely used. They're fairly inexpensive, and you can produce molecular beams that have a rotational temperature of a few Kelvin. All right. And you get free body collisions. So again, we have gas running here. We open this thing up for a fraction of a second. We have adiabatic expansion occurring. Free body collisions occur in the throat, and we very quickly convert all of the rotational energy to translational energy. And the rotational temperature drops from room temperature to, in the middle of the cavity, about 2 Kelvin. Okay, that's ideal, again, because we have so much, we want to minimize, we want the partition function to be as favorable as possible. We don't need to measure 50 lines at this point. We're looking to detect a new molecule. We ideally want the beam, so to speak, and measure higher frequency lines once we have something. But initially, it's not advantageous to dilute the population over any more than the number of levels. Okay. The other technique, which I won't talk about today, but I'll talk about tomorrow, is chirp pulse spectroscopy. This was developed about a decade ago by Prost Pate. And this is something that's a very remarkable technique. We're not doing tiny frequency steps with a cavity. We're doing broadband. What? Oh,
It was a question.
I'm sorry.
Oh, sorry, I just had
Yes.
to ask again. How do you warm up the beam, so to speak?
Yes. You can use things like different buffer gases, for example. That's one common method. I mean, there are various tricks, so to speak. I mean, part of it is you can also sample, you could potentially sample and let the beam closer to its orifice, so to speak. Instead of looking, many nozzle diameters, you could look at it closer in. So different things you can do to try to extend the spectroscopy. The other way to do it is just to use a completely different experiment where maybe the rotational temperature now, instead of 2 Kelvin, it's liquid helium-cooled cell at 80 Kelvin.
So what's the danger of changing the chemistry, though, when you change the vacuum gas?
Changing. Oh, well, no, the point is you have, if you've gotten to the point where you know you found something, then you can sit on the line and you can change parameters, or you can, let's say, go to a line that's fairly high in energy, that's weak, and then adjust parameters to see if I turn the discharge voltage up, for example, would the line get stronger? If I replace the buffer gas, which is neon, with helium, would it be stronger? Right? So there are different things like that you can do. So this is an amazing capability where, again, what we're doing now is we're piggybanking on all these developments in related fields, high-speed digital communications, and in particular. And what we do is you can buy now you have enough money, you can buy these arbitrary waveform generators that are incredibly powerful. You can go at 60, we have a 65 gigasample per second arbitrary waveform generator in our lab. So you can synthesize essentially a wide variety of these chirps. You can then ultimately use a small radar and amplify this radiation. So we have a chirp where we go from, for example, 0 to 10 gigahertz in 1 microsecond. And we run it through this radar, which is just a very, very powerful amplifier. And it will amplify the function instantaneously, this chirp at time. And then we blast it into our cell, and we perform this chirp experiment. We turn the excitation off, and then we have a very, very fast digitizer again. Depending on who you are, if you're the military, you can probably afford to get 100 gigasample per second scope, so you directly digitize the output. And so you get incredible bandwidth. You get 10 gigahertz, 20 gigahertz all at once. Now, you don't have the advantage of the sensitivity of the cavity, but when you exchange sensitivity, you get the bandwidth. All right, so you get this incredibly wide perspective. I'll talk about that more tomorrow. But, so in our case, and in other people's case, what we do is we take this Fourier transform cavity experiment, which is a simplified cartoon as shown here. We use the supersonic molecular beam, but what we're now going to do is we're going to apply electrical discharge to it. All right? And by doing so, we then will inject gas. Now, this is a very low repetition rate experiment because we're limited by the size of the diffusion pump. We have a fairly big diffusion pump. I should point out, everything in Fourier transform microspectroscopy scales on size. So there are people out there, Steve Kugelich, who's now retired in Arizona. He had a spectrometer that went down to, I think, 1 gigahertz. And he had, cavity mirrors that were like 3 feet in diameter, right? So everything scales. You want to go low frequency, you make the mirrors bigger. If you want to go to higher repetition rate, you get a bigger diffusion pump, right? Ours is 8,000 liters per second. You could buy a 100,000 liters per second diffusion pump, right? You have to figure out where to put it. But it's huge. But you can do all this scale. So nevertheless, we are limited, 8,000 liters per second diffusion pump, we're limited to about 5 hertz. So the duty cycle of this experiment is actually really low, right? We're doing 5 times a second. We're doing a measurement for 1 millisecond. So we're doing 5 milliseconds out of 1,000 milliseconds, right? But nevertheless, while we're taking, we have very good sensitivity during that period of time. The point here is the gas will then rush down here. It's a dilute sample of organic vapor. And then we have a self-lighting and self-extinguishing discharge. Once the density gets high enough, the voltage is high enough, the discharge will strike. All right? And in this throat, we get all these collisions. We break chemical bonds, and we ultimately reform new molecules, or we form reactive intermediates. And so by the time it gets here, we could produce molecules which are much bigger than the precursors we started with. So for example, the example I showed the other day was we could take something like cyanoacetylene 8C3N and diacetylene 8C4H, and we can make 8C17N. Right? So we can make really big molecules in the throat of the expansion. Again, there are many things to optimize in terms of the gas concentrations, the voltage, the geometry of your, but you can produce this very rich broth of both familiar and exotic molecules, many which are larger than safety. Or I mean, that we started with, I'm sorry. All right, so there are lots of different ways to then begin the process of figuring out if I have a specific molecule I'm looking for, how do I know that it's there? You could do things like chemical assays, right? So if I know the molecule is, in the case I'll show you, is silicon and carbon, if I take a precursor, it shouldn't depend upon whether the hydrogen is present or if I replace hydrogen with deuterium. All right, that specific species. Is it an open shell molecule? If it is, then if I apply a magnetic field, then the line shouldn't be affected by that. It certainly should be a discharge line if it's going to be something reactive. I can rule out larger molecules by assuming that I mistakenly, if I see two lines saying, well, maybe instead of it's the 1 J equal 2 to 1 and 3 to 2, it's 4 to 5 or 5 to 6. Right? So there are different ways to look for this. There are, in some cases, ways that you can distinguish because there could be hyperfine structure. Again, we have very high resolution, so we can use that to advantage. So look for things, for example, does a molecule contain nitrogen? I use a quadruple. A very powerful method is double resonance, whereby we can link lines together in the spectrum. All right, so ab initio calculations are a key part of what we do, or like collaboration. Again, the idea here is that you can, fairly standard programs, normally predict the rotational spectrum to typically 1% or so. Right? It could be better, it could be worse. And with fairly standard programs, as described yesterday. And using fairly standard desktop machines, you can provide what's most important, obviously, is the structure, the rotational constants, and what's often overlooked sometimes is the dipole moments, and specifically the projection of the dipole moments. So a molecule might have a very big dipole moment, but if its arotational spectrum, or its arotational moment is very small, you like to know that in advance, because the amount of power we use in the experiment depends upon this quantity. And we can, obviously, the calculations can show us the relative stability as well. So typically you get a few percent. If you go to really high level cluster calculations and throw the kitchen sink at it, depending on the species, you can get down to 1/10 of a percent. Keep in mind that what we need for astronomical research is much, much more accurate, right? But the point here is, in a cavity device, if you told me the rotational spectrum of the molecule is, a calculation is 1/10 of a percent. At 10 gigahertz, that's 10 megahertz. This cavity has a ITAMP bandwidth of 0.5 megahertz. So that's 20 seconds of the cavity. I can do 20 seconds of the cavity in 5 minutes, right? So, and then if I can find the line, then all of a sudden that 10 megahertz uncertainty is now a few kilohertz uncertainty, right? So that's exactly what we're seeking to do. We use this kind of bootstrapping method to ultimately find. I will warn you, however, that you always get an answer when you do ab initio calculations, right? And you have to be careful that the answer is actually meaningful. All right. So I will. I changed my clock 20 minutes before I started, so I actually reduced the amount of information. So there's two basic approaches. The one that is very widely used today is that you have an idea of a species you seek to detect in laboratory. Right? So what we're going to do now, we have an ab initio calculation for the molecule. It's very narrowly focused. And we're going to, generally speaking, ignore all other lines in the spectrum if they don't meet the criteria of the molecule that we're seeking, even if they're strong. Because, again, we have a model and we're trying to find the rotational transition that fits that model. But I'll talk about wideband spectroscopy, where, in fact, we're going to just measure everything and then try to figure it all out. All right, so the idea is that we have this iterative cycle. We optimize, we Again, nearly all searches are done this way. We optimize the chemistry in hopes that it will produce the molecule that we seek in high abundance. Typically, we use analogic reasoning, which is the weakest form of reasoning, right? By N as well, if we're making the C4H radical, we optimize its chemistry. We want to make C6H radical. That's probably a pretty good step question, right? So we use different things which we think are related to the species that we seek. We do a search based on the calculations. We detect lines. We try to assign in the spectrum that we measure everything that we can. Is the remaining lines, do they have some unique structure that might tell us about what the carrier is? We need to test the remaining lines using the most important descriptive first. For example, if it's a magnetic molecule, we want to look at all the lines and see which ones are magnetic, right? We can do isotopics. Then we're going to do related measurements. And the key point, repeat this, and the key point at some point, fairly quickly, the model should be predicted, right? We should be able, on the basis of a small number of measurements, to ultimately use a simple rotational Hamiltonian and predict even more lines very accurately. And the key point here is confirmation then becomes detection of a rare isotopic species if necessary. Again, in this process, we're throwing out lots and lots of lines that don't be everything here. All right, so let me just show you now about, as a specific example, about SICSI. It turns out there's 3 reasons why we'd be interested in this, only one of which is astronomical. The first one is it's thought to be fundamentally important. It's the only cluster of silicon carbide with 3 atoms whose structure and bonding has not been measured previously at the limited laboratory condition. It's well known to be highly stable as a product in evaporation of solid silicon carbide. And as I'll show you, chemical equilibrium calculations have also long predicted it to be very abundant in IRC plus 216. And excuse me, the point I think of Daniel yesterday about the role that it may play in silicon carbide dust formation. All right. So I won't go into this because it's really not the focus here, but these are the 4 molecules, C3, SiC2, Si3, and Si. These are all well known. This is the SiC2, which is very prominent in space. It was actually long thought to have a different geometry. It was thought to have a linear molecule, SiC. Rick Smalley, the last measurement he did for C60 was to show, in fact, that prevailing view of its structure was wrong. It had this T-shaped structure. All right, half the levels were missing. It had C2 symmetry, and then half that is the people found this molecule in space. But it's a very fascinating chemical system because it's SiCSI is actually very like C3. It's got this very low frequency bending. So as you begin to bend this molecule, you get this interesting effects in terms of how the vibrational pattern changes. All right. It's been known. I think the reference, the date on here, I think this is 1950. People have shown years and years ago that if you just heat up metal, silicon carbide metal, it'd be hard to beat here. But one of the 2 most abundant polyatomic molecules that come off are SiC2, the aforementioned molecule. I should point out SiC2 is the carrier of the neural Sanford bands in the spectra of stars, so it's also optically very well. And the molecule seeking SiCSI. And finally, people have long calculated this species to be a very important, very abundant near the photosphere of the source IRC plus 16. This is from 1992, and this is again a model that attempted to look at the silicon chemistry near the photosphere. We know, in fact, the beta winds of these HGBT stars, as Lucy mentioned, are one of the 2 major sources for interstellar dust grains. We know, in fact, that still macroscopic lines of silicon carbide are observed fairly close to the star itself. We know this is a characteristic emission in the infrared, which is thought due to these. So SIS is well known in the source. I think Lucy mentioned that SiO is, SiC2 is, and you see here, at least by this prediction, it's one of the most abundant small molecules near the photospheres of the star. Okay. There's another calculation shown here. This is now again looking at the height and temperature and as a function of different species. This is the relative abundance, and you see near at low temperatures, 1,000 degrees or so, SiCSI is one of the most abundant small molecules. Okay, but its spectrum, rotational spectrum hasn't been known. Again, just maybe reinforcing what Lucy said yesterday, there's about 5 sources that people in the field constantly go back to, in part because, again, the telescope time is competitive, so you want to go ultimately look at a source where you think you're going to be able to find this molecule. Half of the molecules observed in space are observed in iris samples. All right, roughly half. All right, it produces, it's a dying star, central star is Leo, which is expelling a tremendous amount of gas and dust. Most of the heavier elements are produced in triple alpha processes. In this source and other ones, it's the brightest object in the infrared. It's a carbon-rich star, and we can actually do incredible time-dependent chemistry because it's sufficiently close to us. Okay, and all sorts of metal-bearing cyanides, carbon chains, and megamites and other things. So this is a spectrum. You call it time-elapsed spectrum of IRC. So what I'm just doing here is the same spectrum, I'm just blowing it up, right? And another way to think about this is if you show it as a function of time, the top would be kind of the spectrum you would see in 1975, would be dominated by these very strong components. With, again, better telescopes, more sensitive instrumentation. What was a simple spectrum 30 or 40 years ago is now, it's not confusion limited, but it's incredibly rich. Right? What's amazing about this source is that you can, it's close enough you can use powerful reformers. All right, and what we know is that much of this rich chemistry of these radicals and ions occurs in this outer surface shell of gas and dust. But we know much closer in that we get macroscopic grain formation. Right? So this at the bottom is the log plot. So we know we have dust nucleation, dust growth, and ultimately photochemistry out here. So this is a log plot, right? So we're going from 10 to the 15th down to a few hundred particles per cubic centimeter. The temperature drops from 3,000 degrees to 20 degrees. So a tremendous amount is happening in this inner region. And in the plateau de Viera, the SMA interferometers, we can very crudely understand this spatial structure, right? And so we can map out like many molecules over here, and very small number of molecules are closer to the central star. With ALMA, our picture then becomes this, right? So that the ultimate resolution of ALMA as applied to IRC will allow us really to understand, literally like an onion, we can look at the change in the chemistry radially from the central star. And we can potentially really understand dust nucleation and dust growth because this process occurs much, much closer before we hit the terminal velocity. All right, so as an example, this is just data where we compare the single dish IRAM 30 meter and ALMA cycle 0. I should let it showing up. All right, so it's you can see it better on these displays, but there's red and there's black. So red is the single dish data, and black is the the ALMA data at 0.6 arcsecond resolution. And you can see it allows us that we're not looking at the outer circumstellar shell. We're looking here how close to the central star. So things that are very prominent in the outer shell, like this radical, are not observed close enough. Meanwhile, you see all these lines, and this has a double peak collection. Again, this is the Doppler effect. We're in the outer shell and it's expanding out. Most of the lines, in fact, are U. U means unidentified. And they have a single, a very simple line shape, meaning they're really close to the central star. We don't know what all these U lines are, right? And there are lots of them, right? But we do know that we have all these small stable molecules here, so like SiO, HCN, we can see HCN up to 10,000 rotation. SIS up to 10, et cetera, et cetera. So the question is how, in fact, the key question is how is this nucleation process occurring? And that's where SI and CSI is thought to be important. How are we doing for time? Oh,
10-ish minutes.
I gotta speed up. Anyhow, so there's been a lot of work on this system. Again, like SiC2, people initially thought it might be linear. It turns out not to be. The consensus is now that it has a C2B type structure. It's a shallow bending potential structure with a modest dipole moment. People looked for it in the optical and seen it now. Our group has John Miner, and it has been observed in the infrared. So how are we going to detect this? It turns out it's deceptively hard, it's deceptively difficult in the sense that it has very few low frequency transitions. All right, so it has C2B symmetry, we have two equivalent bosons, so half the levels are missing. It's got again, it's just bent, so the transitions that we're seeing are B-type transitions, so it depends upon this angle. So at 2 Kelvin, our spectrometer, unlike Lucy's, doesn't go to 80 gigahertz, it goes to 40 gigahertz. So if we, or 90, sorry. These are the predicted lines between 5 and 50 gigahertz, assuming 2 Kelvin rotational temperature. So the very faint lines, a really strong line that we like to detect is this one here at 45 gigahertz. Okay. It's challenging, as I already mentioned, because its low J spectrum is very sparse at low frequency. We have C2B symmetry at the shallow end. There's a couple factors that really have to be considered. First of all, if you change the angle by 1 degree, you shift the spectrum by 2 gigahertz. Keep in mind, again, the cavity has an instantaneous band of 0.5 megahertz. Right? So you have to, it's desirable to know this bending angle to ideally a degree or better, if possible. That's an example of just how much the spectrum would shift by 1 degree. Second, which we haven't talked about, is zero-point correction. That is, calculations normally are zero-point calculations determine the equilibrium rotational constants of the molecule. Experimentally, we're measuring the vibration average. So zero-point vibration is an important correction. And in this case, it also shifts the spectrum by 2 gigahertz. All right, so we need to account for that as well in this calculation. So the strongest line here is at 42, which is just above the frequency range of our device. I won't go into it, but another technical challenge that Lucy mentioned is that silane, which is really an ideal source for silicon atoms that can be used for this experiment, at high concentrations pyrophore. Right? That means it burns in there.
Yeah, I was about to ask, how are you making this? Like, what would you think?
I'm going to tell you in a moment. But the beauty is that, and that's why, in fact, like in Japan, in academic laboratories, you can't use silane. Some of the worst industrial accidents have involved silane. If you have a high concentration of silane and you leave the tank open, you're gone. I mean, it will explode, right? But as I'll show you, in our experiments, we have highly diluted samples. And it turns out, it depends upon the movement of the buffer gas. But if you buy, for example, silane and neon, silane and argon, below about 0.5%, it's not pyrophoric at all. It's just considered essentially just like any other inert gas. And in our experiments, we're typically using in the experiment 0.1%. So we can get away with actually buying a diluted sample, which is not at all dangerous. So this is the spectrum, all right, that we have access to. So we can't look for this line. So what do you do? Any ideas? What would you do? Okay, the answer is you cheat. Well, no, the answer is essentially all the most abundant species or isotopic species are always heavier than the normal isotopic species. So what you do is you don't do the normal first, you carbon-13. Everything is heavier, so it's going to shift the spectrum down. It shifts it down about 10%. So instead of 42, it's at 38, that transition. All right? And therefore, we can then, well, ultimately, the transition that we're going to seek to find is at 38 gigahertz, which is well within the range of our device. So that's what we do. So we optimize the chemistry. We use dilute silane, and in this case, you can buy, or could buy, doubly substituted isotopic acetylene. So we actually then have to measure, which wasn't known, which is trivial to do, but we measure the rotational lines of the doubly substituted SiC2, which spectrum is now well known. We optimize the chemistry to produce that line in high abundance, hoping that it's going to produce SiC, SI in high abundance, right? And we do a search. I don't have much faith in our theory, friends. So instead of, we just scan like 2 gigahertz, right, to cover everything. And these are the lines that we observe, right? And it turns out some of them are known. SiO is you get oxygen in these experiments very easily. So you can form these SiO molecule, and it's highly vibrationally excited, as shown here. The strongest line, which we could not assign at the time, is indicated here. Right? And the initial prediction is here. So now we can look at every line that's not assigned, And we can begin to do tests. For example, the molecule we're seeking doesn't contain hydrogen, right? So if I replace silane with deuteridine, which you can buy commercially, the lines should still be present, right? If the line changes, then if the line disappears, that means it contains hydrogen. It should depend upon both precursors. I can pull one precursor out and the other, the line still persists. Like in the case of Si3, you can rule it out. It should be non-magnetic, it should be discharge dependent. So then the question is, it's a question for the students, how many lines do you need? How many individual rotation lines do you need to be certain for an identification? So a show of hands, everyone think it's 5 or more. No one's raising their hand. How many think it's 3 or more? How many think it's 1? The answer is not a student, but in the back. The answer actually is slightly cheating, it's 1. And the reason you can do this is because you may not know the rotational spectrum, but you can be very confident in identification because you can do isotopic spectroscopy. This line is really strong, right? So silicon has the advantage, it has 2 isotopic species, silicon 29 and silicon 30, right? At 4.7% and 3.1%. This is strong enough. If this is the correct identification, I can have a theoretical calculation of the structure. I can correct that theoretical calculation. I can scale it to the measurement that I have here. And then I can say, well, what happens if I replace one of the silicon atoms, 28 with 29? I can predict the isotopic shift. And I have enough sensitivity to detect it, right? So I can then optimize the chemistry on this line. And if this is right, then within a reasonably good accuracy, I should be able to find another line down by that ratio of intensities, which is silicon 29, and ultimately silicon 30.
Technically, you do 2 experiments.
No, it's the same line. It's the same line. It's the same rotational line, right? But it's a different isotopic species.
2 lines.
Right? And so that's what you can, and the beauty of the isotopic shift, especially, it's not a hydrogen, so it's a heavy atom. You can predict the isotopic shift to 1%. So if the line is supposed to be shifted by 100 megahertz, that line should fall within plus or minus 1 megahertz. So it's actually a very precise prediction. And so that's what you can do. And there's another advantage of doing this. The silicon 29 has a spin of a half. We're doing high resolution spectroscopy. So in fact, the line that we observed at exactly the right spot, shifted in frequency, has this additional, this is the Doppler effect from the instrumental on the experiment. And you see it's just 10 seconds of integration. You can barely see the lines here, right? And this is silicon 29, which we search for on that basis. And it has this extra splitting here. And this extra splitting arises because it's nuclear spin rotation. The fact that silicon has a spin of a half, which we can resolve. This is the endo-red location, how it interacts with this very small magnetic field of silicon. So that was very encouraging. We measured silicon 30, and then we optimized the chemistry and ultimately found more lines. And we did isotopic spectroscopy of those lines. So really, after 3 or 4 lines, we have now the rotational transitions. Yes?
So I wish to point out at higher frequencies where you don't have a beautiful FT spectrometer with high sensitivity, you cannot see isotopic logs in natural abundance, and therefore this trick does not work. But
you could do you can
buy samples and do
Yes,
isotopic
yes.
substitution.
We did look into buying all silicon 29 silane.
Yeah.
It was about $75,000.
Yeah.
That actually is, I digress, but that
For
would be
how much?
actually, what's that?
For how much?
It was a small tank, so it would have run probably, it's hard to say, depends on the consumption, but maybe a year of modest use. But it's nothing compared to sulfur 33, which we wanted to do. An unnamed company sent us a quote by fax for $450,000 for 100 milligrams. And we didn't buy it. That would have been the entire Renaissance grant. So. Anyways, I'm now really running out of time. But so ultimately, we measured a number of transitions under these conditions. Now we measured the carbon-13. We haven't measured them all, right? But again, by the scaling argument, we can scale now, and we can now predict the rotational transitions of the normal fairly accurately. We can then replace carbon-13 with carbon-12. We can do that experiment. And what we found, what was crucially important, is in addition we did the measurements, the range of device, we can do double resonance experiments and extend the spectroscopy further. And it turns out, a key point here is, in fact, rotational temperature is not 2 degrees. It's actually much higher in this experiment, probably because SiC2 is not rotationally cool anymore. So we could see transitions that were something like 85 Kelvin, right? So these are all the transitions, and for silicon-29. So we can then, we know the rotational spectrum very precisely. I won't go into here, but it turns out we can look then at how the rotational transitions change with isotopic species. There are various corrections for rotation vibration that we can calculate. Again, it's a very floppy molecule, so vibrational perturbation theory in second order doesn't work very well. We have to use variational calculations. And that's because, again, this bending motion of this molecule is highly anharmonic. I won't go into too much detail, but that, again, theoretically was a very interesting comparison, because we could measure all of these isotopic species. We could measure vibrationally excited states as well. And ultimately, it's of no astronomical consequence, but we now have a very, very precise structure for this molecule based on combination of theory and experiment and correcting the rotational constants of the effects of zero formation. And you see here the best estimates are very precise now. Okay. Look at the vibrational satellites again. Those differ depending on how we calculate the vibrational corrections. But it turns out that's not good enough for an astronomical research, because we just measured the low frequency spectrum. In IRC is typically tens of Kelvin, so we need to extend the spectroscopy to the millimeter, right? The beauty is we have a rotational spectrum. We have, this is what we actually call the nuisance parameters, right? The fact that as you begin to wind up this molecule, it distorts through this, going to centrifugal distortion. Right? So what?
Beautiful.
Well, right? So again, this is not of chemical interest per se, but astronomically we need these numbers because we need to be able to predict the lines to a fraction of the line within IRC. So we need to know these centrifugal distortion classes very precisely. And again, from the low frequency measurements, we can then extrapolate the high frequency. And these searches then are very, very modest. A few megahertz, 10 megahertz, something like that. So that allows us again to pin down the rotational spectrum, determine these high order centrifugal distortion constants, and give a very precise spectrum, so that we either have measured or can calculate all of the most astronomically most interesting lines to a fraction of a line. All right. Within 1 week, our collaborator, Pepe Chinocharo, detected ultimately 110 lines in IRC. Okay. The data was all there all along, but assignments from the laboratory spectroscopy then made the detection of this species possible. And these are just a small number of lines that he had identified or assigned. You see, they have this, it doesn't have this classic double repeat line profile due to the download effect. And in fact, there are lines in the SMA survey which we could use, and we could do some crude mapping. And what we find, in fact, is that it has a fairly compact emission. Right? So keep in mind the outer circumstellar shell. This is 5 arc seconds. The outer circumstellar shell is out here. Okay. So that means it has some extended distribution, but it's fairly close to the center star. You can make these rotational temperature diagrams that Susanna mentioned yesterday, all in hundreds of lines, and it looks like there's several different zones in which SiC exists in. And it appears, in fact, that it is produced precisely, it's concentrated near the central star, it's an extended emission, and its abundance peaks in this so-called dust formation zone. So, in fact, there's every reason to believe that SiC is, in fact, a key nucleation agent for silicon carbon gas bands. The tricky part, however, right, is that its abundance is comparable to SiC2, but its lines are 100 times weaker. It's got a smaller dipole by a factor of about 4, the square root of 16, and it has a larger partition function. So that makes its lines harder to see. Okay. So I'm out of time. But that's just one example of where, again, we're trying to do a laboratory experiment based, in this case, astrophysics, where we are seeking to identify a molecule which, if we can find it in the laboratory and ultimately in space, it can tell us, it can be impactful, right? We can learn something about the chemistry of physics, in this case of IRC, and begin to better understand this whole dust formation process, which again, this is just one molecule in a whole series of species which ultimately should be found. in the laboratory, then we can shoot in space. So the next lecture is going to be a completely different approach than this directed approach, where we're specifically looking for a molecule, and then we're throwing lines out that can read it. In this case, I'm going to talk about work that we've done where we just, in fact, take the entire spectrum, and we want to figure out the identity of everything, and it requires a whole different set of tools. And we don't want to spend our lifetime doing this. Right? We want to develop fast automated tools. We really want to do this library for unification, right? Which is a really powerful capability if we can do it. And this gets into issues like information theory and machine learning. And people don't know already. People invoke this character here. This is Donald Rumsfeld. Does anyone know who Donald Rumsfeld is? No.
That's a known unknown.
Correct. We're talking about known knowns and known unknowns and unknown unknowns. And I'm going to show you how we can really adapt this with good success to this exhaustive analysis of benzene, where we see about 200 different species. And we can identify them. So, with that, I will end. Questions?
More questions?
Yeah, I wonder what the bending vibrational frequency is. Approximately.
Of this molecule?
Yeah.
I forgot. I don't know if it's on the slides.
If you had mentioned that as in C3,
It's like 100, 150 microwave. You see it's in that. It's a board. It's under 200 there. The bending mode, it's something like 2, it's under more than 200. So it turns out that's actually a problem. If you bend it more than about three bending, 3 quanta, it's almost lethal.
Besides the astronomical interest,
Yes.
obviously, is there an interest that you've noticed from maybe like the organic synthetic community about what might be like reactive intermediates, like the structures of these possibly reactive intermediates?
You mean the silicon or just in general?
In general, yeah, like what you can see in the discharge, actually. Study.
Well, I think there's a lot of potential for that. I think part of it is that we're doing these experiments because they don't mimic what's occurring in space, but it's a way that, by experience, we found by analogy that we produce a lot of molecules. So I think they would like, a lot of the chemists would like more quantitative analysis under more conditions that they feel more comfortable with, right? Electrical discharges are just notoriously difficult to understand in that sense. But there are, I think we're getting, as I'll talk about more, I think we're getting the capability now that we could, under a very specific set of reaction conditions, we can ultimately analyze everything that's there. And then we can compare the production of different things. So the problem here is there's all sorts of other molecules being produced, and by this method, we don't really know what their relative abundance is, and how much can you change the chemistry to make one thing and not make the other. And with this much broader view, I think then we can develop really a comprehensive picture of how all these things are linked together, which I think will be the chemical much more useful. So I don't know if that answers your question or not.
Yeah.
I wonder why you're just interested in chemical bonding, like a bond that why you consider other properties of bonds?
Well, no, it's not that we're not interested in that. It's not, we just can't measure that. We can't measure the bond strength, right? I mean, so these are the things that we can measure from our experiment, per se. So we can't.
So, like, in one of the slides, you showed the computational and also about the bonding and different computational chemistry model. So, you can measure all the properties, like each chemical bond individually.
Theoretically.
Yes.
Yes. Yeah. Oh, absolutely. Yes.
I
Yes,
mean,
yes,
like,
yes.
we should not be considered
Not consider I'm sorry.
all the properties of the bond. like the vibrational mode, the local, not the normal vibrational mode. The
Yeah.
local vibrational mode of the check can affect the bond
Oh,
and the estimate of the bond.
yes.
I'm talking.
Yeah, compilation, yes, yes.
Yes.
Yes, I mean, these were very, these were calculations done by our collaborator, John Stanton, and other people. And they added many different corrections. I don't know exactly to what, at what level they cut off the correction, so to speak, in terms of how it affects the rotational spectrum of the local species. But yes, I mean, ultimately, a series of corrections which should be applied.
Yeah.
To,
In terms of the bond angle.
yeah,
We also can measure the bond length.
yes.
At the, this vibrational in a different level.
Yes. There you go. So we've done vibrational spectroscopy. We've done rotational spectroscopy at various vibrational levels as well as part of this work. That turned out to be more difficult because obviously the lines aren't as strong, and in fact, the full spectrum moves up in frequency, and we don't have a 9-degree grid system. So it's our ability to actually probe the vibrational pattern much above 1 or 2 delta is very limited. But potentially it could be, there are other techniques, optical spectroscopy infrared, which is not what we want to apply to this. Could really map out much more exquisitely the whole vibrational and electronic structure of this particular species. So again, initially our interest was just the ground state from the point of view of can we find it in space. And now we can extend that, for example, to can we see the vibration excited states in space, right? Or how can we extend the spectroscopy? It depends. I mean, there are different ways we can go, right? Theoretical chemists are often interested in electronic and comparing their calculation to the experimental structure, for example. Right? But astronomers don't care about this. First setting about those wires. Good question.
It's possible to record the rotational spectrum for excited electronic state?
Excited?
Electronic state?
Yes. I mean, in our experiments, we don't populate these electronic excited. So you could do, for example, microwave optical double resonance.
Yeah.
You could excite a molecule to an electronic state and then do microwave spectroscopy and try to determine the rotational constants or the rotational energy levels in that electronic state. There are people who do that. What's that? Yeah.
And there is an average lifetime for that excited state? Or
Yeah, there are issues along those lines, yes, about how, is the state, it's lifetime issues relative to the time scale for doing the microwave experiment. But, like, for example, I didn't show it, but you can, SIC2, you can do microwave optical double resonance. You can begin to probe rotational transitions, get microwave accuracy in the upper electronic state. But for much of the work that, again, we're interested in, it's ground state rotational. But yes, these things can be extended, absolutely.
So you mentioned that electrical discharges are notoriously hard to understand.
Yes.
So if you're starting a new project with, say, a molecule that's never been seen,
Yes.
where do you start? What do you look at? Do you look at bond energies? Do you look at, like, where do you start?
Your advisor texts Mike and gets advice.
Well, you really, I can answer, it's almost too hypothetical.
Right.
You have to, it depends. Is it, the molecule seeking, is it a metal-bearing molecule, right? Is there, ideally you would like to be, is there a possible gas phase synthetic precursor you could use, right? So you could use silane, or you could use methane or methanol. There's various carbon, obviously, many carbon. There's sulfur, carbon disulfide, or H2S. It totally depends. My preference would be using gas precursor if you can, as a starting point. But it may be totally practical. If you're looking at vanadium oxide or whatever it is, you have to heat up, you have to avoid vanadium. Aluminum is kind of in between. There are potentially some aluminum gas phase species or precursors you could use, but also you definitely consider ablation. So,
In terms of like voltages and currents, you just have to develop an intuition over.
well, again, this is the analogic reasoning, so to speak. You have to, ideally, you would want to try to optimize the chemistry on something which you thought was related in some way, right? So for example, you could ultimately, you want to do, I forget, like in a laser ablation experiment, we did something on germanium dicarbide. So what we did is we optimized the chemistry on silicon. Right? We had a silicon rod in, we optimized everything, we optimized the flows, the concentrations, laser power, everything. And then we simply swapped in a germanium rod instead of silicon rod, right? And we recorded the spectrum. So there's all, I mean, that's what you have to do a lot in hopes, and there's a lot of parameters. So what I didn't mention, what I should have mentioned probably, is that this was like the fourth attempt on this experiment, right? So I didn't, I don't, there are lots of projects that we do that don't work out. It's not that fundamental. Maybe we were seeing the wrong one of the right? And so part of it is really just getting the right conditions. Because normally what happens is once you find something, you almost always can make it better. In some cases, much better, right? But you just need enough signal where it's like C60, right? People discovered C60 before small photo. The exon group that has a mass spectrum. You can see the mass spectrum. There's a little peak at C60, but it's not prominent, right? What they found, it was fortuitous, maybe it was just because they were, more whatever it was. They pursued that, or maybe, more prominent. So that's what we kind of realize is, discovering that, I won't talk about negative ions, right? We looked at spectra 20 years earlier, you see rotational line, C4 minus, right? If we were smarter, we would have done this 100 years ago, right? So that's scientific process. Exactly.
With that, I think it's time for Mike to take a short term.
4.5 minutes.
If you have questions.